Okay, I think we can start now. So we're very happy today to have Zhewei Yin from Northwestern and Argonne telling us about entanglement, entropy, and elastic cross sections. Please take it away.
Thank you. Thank you very much for having me here. It's a pleasure to be here. So today I will talk about the two recent works in collaboration with Yin Lo, also at Northwestern and Argonne. And the title is Entanglement Entropy is Elastic Cross Section, right? And this seems like too broad, too general statement. So you may expect that there are some asterisks here. But and I will go into that. But it turned out that in the end, you don't really have a lot more, a huge amount of asterisks. Actually, this statement is actually indeed pretty general, and we'll see. So why are we talking about entanglement entropy? So firstly, we know that the entanglement is a key phenomenon in the quantum field, in the quantum theory. So it is a key property that separates quantum theory apart from classical theory, right? And one of the key quantities that you can quantify is the entanglement entropy. And we are also familiar with the entropy as extensive quantity. Usually, when we think about entropy, we think about a system with a lot of particles in it, or a lot of degrees of freedom in it, and it is aggregated somehow. And we also know that there are area laws for entropy. So the most familiar one, maybe the first one, is the Bekenstein-Hawking entropy for like gravitational systems. But that was like in the 70s. But after that, there are also people also have discovered area laws for like field theory examples. Either through ADS-CFT or through lattice simulations. But in any case, these are indeed like the entropy for extensive system. Okay. So, but now let's consider, instead of this system, let's just consider the scattering of particles, which we are very familiar with. So if you consider the entanglement in the particle scattering, actually this has people have just become interested in this like in the past like 10 years, I would say. And in terms of experiments, actually only very recently people looked into experimental data, and you see that last year and this year, ALAS and CMS had the first observations about the entanglement in like particle scattering. So what they do is to measure the entanglement between the final state TT bar particles and to see the entanglement of the helicities. Okay, so it is observed very recently, and people become interested in it because you can see it as a constraint on your theory. Okay, so maybe you say that your theory somehow maximize or minimize the entropy, and if you entanglement entropy specifically, and if you put this as an assumption, somehow it can give you some unique theories. For example, there are the seminal papers that found out that for some of the processes in QED, actually the entanglement entropy of the final state is maximized. And there are also some other papers also discovered that in, for example, in classical black hole scattering or in strong interactions or like in the model theories like the established models and so on. And it turned out that people can. It turned out that some of our very familiar theories are actually minimize the entanglement entropy in some scattering processes, and you see that so there are a lot of people about this. The people in the audience also like Carlos also did something about this as well. Okay, so but all of these are for some very special series, and the idea is just to see whether from assumption of maximize or minimize entanglement entropy, we can get some specific theories. But actually, what we are going to do is to take one step backwards and ask the very simple question. So, for a general 2-2-2 scattering, what is the entanglement entropy in the final state? And actually, there are also papers that probe these questions here somehow. And these series of early papers are really usually what they do is do a perturbation theory in terms of coupling and do some tree level. And they do have some tree level results, but nothing very general or very universal. And today, this is what we are considering today. So we are considering just in the general 2-2-2 scattering, what is the entanglement entropy in the final state, and it turned out that we can indeed get some very universal and very general statements here. So you will be able to see that just from very simple ingredient, we can get a very universal and very general relation. So the first ingredient for us is just to say that we have a two-particle scattering where the initial two particles are distinguishable. Okay, so which means that apart from the momentum, they are separated by some quantum numbers. For example, spin, it can be charge, and so on. It can be mass, and so on, right? So then, for example, we can construct a state. Then the state is a product of the particle, one particle states, the particle A and particle B, and we say that there are some quantum number that separate what A is and what B is. Okay. And then, if you want to compute the entropy, the first thing you need to construct is the density matrix. Okay, and here we say that this density matrix we need to normalize it so that the trace of it is 1. This is basically the unitarity constraint. It's saying
is it important that initial state is a pure state?
For now, we just consider this very general. This is a very good question. I would say. For now, we will just say that. Here, these two particles are distinguished by some quantum numbers, and then apart from that, there is only the data of momentum, and it is practical to say that usually the momentum are not entangled. And here, indeed, we are assuming that the initial. Okay, so there is whether there is initial entanglement and whether there is a pure state. The initial state is
the way you write it. The
yeah. So this is indeed a pure state. Here,
okay.
for I would say for almost all of my talk, I will talk about the pure initial states. And if I have some time, I will also talk a little bit about mixed state, and there is some interesting results there as well. Okay, but mostly I will focus on pure state. And I will focus on the initial state where, for now, we'll just say that the initial state, the initial two particles are not entangled in any way, so that you can see that it's just a product. Okay, so now the intuition here is that usually when we have two particles colliding in an experiment, usually they are not entangled in terms of momentum. Okay, all right. And then we need to normalize the density matrix so that the trace is 1. This is basically saying that the total probability is 1. And then the thing is that you may now you need to say that these are basically the wave function of your in terms of the initial momentum, and you may want to say naively that you may just want to use the momentum eigenstates here. But it turned out that that is not very good because the momentum eigenstates, you know that they normalize to a delta function, right? So the delta, there is basically a divergence here. So if you just use the momentum eigenstates as your initial states, then you will not be able to satisfy this this normalization constraint. Okay. So what we do is to regulate our initial state with a wave packet. Okay. And this is one way to do it. For example, if you read the textbook, another very general, common way to do this is to do a volume regularization. So by saying that we put our plane waves in a box, and then in the end we take the limit of the box, volume of the box go to infinity. But this is not what we are doing here. And basically, this is the key difference between our paper and all of the results before, because usually when people before people usually use the volume regularization, and I would say the good thing is for the volume regularization is that you can it is intuitive and you can get results very quickly. But however, it is very hard to know quantitatively what the result means. So I would say that it is a good way to get some intuition. But in the end, if you want to make things precise, it's not actually a good way to do things. And also in practice, when we do experiment, usually we are not doing it in a box. Instead, we really do have particles that concentrate in some wave packets. So this is also more realistic. So you see that this is what we this is actually the key point of our paper, which is that we are using wave packets to regulate the initial states. So the second ingredient we have is that we are assuming that we have a scattering. So here we have a S matrix, and we just we don't impose any constraint on the theory other than the S matrix is unitary. And then my final state will just be the S matrix acting on the initial state. And as usual, you separate the S matrix into one part where there's no interaction at all, and there is also a transition matrix here. And from the unitarity of the S matrix, you will be able to derive the output theorem, which we will use heavily. Okay. And from the transition matrix, it is also we also know that it is related to the scattering amplitude. So now this final state with the S matrix acting on the initial state, so it will give you the complete final states in the sense that in general it can contain for example, one particle final state, two particle, three particle, and n particle, and so on, right? And also, even if it's for two particles, it does not necessarily have to be particle A and particle B. It may be some other particles, it may be two particle A's, and so on, right? So this is the complete final state density matrix, which is just you use this out state. But this is not what we are considering. We want to consider some similar final state, where we say that we only select the elastic part. By elastic, we means that the final state will contain will only have two particles, and one particle is particle A, which means that it has the quantum numbers of particle A. And the other particle is particle B. This is what we define as the elastic final state. And then how do we get the initial elastic final state? What we do is that we put a projection operator PAB here, where this PAB projection operator just selects your final state. Okay, so it selects the final state with two particles, one with a quantum number of A and the other with quantum number of B. Then if you do that, then once you have the states, the first thing you can do is compute some probabilities. For example, this P total is the square of the transition matrix acting on the initial state. Okay, so this P total is the total probability for any scattering to happen. Okay, and the other probability you can compute is the elastic probability. So you after the scattering, you put a projection operator here. So and then this probability is for an elastic scattering to happen. Okay, and similarly, you can have the inelastic part, which is just everything. Is that you have the scattering, but the final state is anything other than AB. Okay, and it's very clear that P elastic plus P inelastic is P total. So but here the P total is not one, because you know that the S matrix has one part, right? That it will dominate. So the dominating outcome will be just no scattering at all. But this total probability is for some scattering to happen, so it is smaller than one. Okay. So then our third ingredient is that we are taking the plane wave limit. So although we start with initial states were described by wave packets. In the end, we want to take the limit of the plane plane wave limit, which just means that we are taking the limit of the momentum eigenstates. Okay, so how do we do that? We say that for the initial states, the wave packets are centered on some momentum. So now after once we do that, then we can go to a center mass frame in terms of this momentum, right? So in the center mass frame, we can have some we can describe the kinematics of the initial particle using only one momentum now. Okay, and now this is basically what is the center of our wave packet. And then there is there is the weight of the wave packet. Okay, so for the waves in the momentum space, we are saying that the wave is characterized by delta p in the direction of motion and the delta t in the transverse. So basically, so in the momentum space, we are having two waves for the wave packet, one in the transverse direction and one in the direction of momentum. And here we made the assumption that this delta p is the larger one. And this delta t is at most as large as delta p. The reason for this is very intuitive, because we know that when you boost the wave packet, then it will be Lorentz contracted in the longitudinal direction in the position space, right? So in the position space, so these waves are for momentum space, right? So the inverse of these waves will be the waves in the position space. So in the position space, the waves in the longitudinal direction will be 1 over delta p. And the waves in the transverse direction will be 1 over delta t. So now because the Lorentz contraction, then the 1 over delta p should be smaller than 1 over delta t. That's why, that's the motivation where we have the delta p to be larger and the delta t to be smaller. And yeah, and we also define something 1 over delta t as L. So this L is basically the transverse weight of the wave packet in the position space. Okay, and in the center of mass frame, of course, both the initial particles are boosted if we are in the center of mass frame, right? So now what we mean by taking the plane wave limit is just saying that delta p is smaller than this the size of the momentum, so that we can expand around this small parameter delta p over k. All right. So now remember that the first thing we can compute for the final state are these probabilities. And now the thing we can do once we define what the plane wave limit is just to compute these probabilities in the plane wave limit. And we are interested in the leading order piece, leading order non-Venetian piece in terms of delta p over k. So they are so in this case, once you as long as you see a dot above equal sign, that means that we are taking the leading order term in the plane wave limit. Okay. So in the plane wave limit, you see that the probabilities are just proportional to the cross sections. So the total probability is proportional to the total cross section, and the elastic probability is proportional to the elastic cross section, and so on. Okay, and then the factor in front is a universal factor, and this universal factor is an integral of your initial wave packets. And the thing is that just from a very naive dimensional analysis, you know that this universal factor I0 should have the dimension of 1 over the area, right? Because the cross section is the area. So it turns out that you can argue very generally. You can derive, I would say, you can derive very generally that this I0 scale as delta t squared. So it actually is independent of the width in the longitudinal direction, but it only depends on the width in the transverse direction. And it scales as delta t squared. And remember, this delta t is the width in the momentum space, so it has the dimension of mass. So this is mass squared. Basically, that's the inverse of the area, right? And it turned out that you can derive very generally that this I0 depends on the overlap of the wave functions in the transverse directions in position space. So the first thing is that it is 1 over the area. So what is this area? This area is just the area of the wave packet, the size of the wave packet in the position space. And then it is 1 over this area times some factor. This factor is the proportion where the two initial particles are overlapping. For example, if the two, so suppose my two hands are the two wave packets, right? For high duplication is something like this, and they fully overlap. Then you have a factor of 1, for example. If it's not a high duplication, you only overlap part of the wave packets. Then you have this additional factor, percentage overlap in front. Okay, so I would say these are all pretty abstract, but the thing is that we can do this very generally. We don't need to specify any of the details of our wave packet. But you see that this is very abstract, and indeed we find it very helpful to provide an example of our initial wave packet. This we will call the transversely uniform pancake. Okay. So what specifically what we are doing here is that firstly, in the position space, we say that we constrain our wave packet inside the box. So which means that outside this box in the momentum space is 0, inside the box is non-zero. Okay, and this box has the side length of like 2 delta p. Okay, and then the wave packets basically for the wave packet we can choose whatever we want, and we choose what's most convenient for us. And the most convenient for us in the longitudinal direction is just to say that in the longitudinal direction is uniform. So then if you do a Fourier transform and go to the position space, if it is uniform in the momentum space, in the position space, then it will be something like this. So you have a peak here, but it's unbounded. Okay, because it is bounded in the momentum space, it will be unbounded in the position space. Okay. However, in the transverse direction, we really want to do a pancake. What do we mean? We want something in the position space that is roughly uniform inside our pancake, but 0 outside. The thing is that once we constrain our wave function in the momentum space inside this box, you know that it cannot be bounded in the position space, right? But still, we want it to be bounded in position space inside this pancake transversely. So the way is that we can do this approximately. This is saying that in position space, we say that in the transverse direction, the size is L, remember, right? So we say that this L is a lot larger than 1 over delta P. Then what we can achieve is that it is roughly uniform inside this area A, and it is roughly 0 outside. So if you, so for example, the density profile will be something like this. So you see that it's roughly uniform inside and roughly 0 outside. Although this is still unbounded, to the leading order, it is bounded within this area A. Okay, and here the only thing we specify is that we need to specify is that this area is A. Well, actually, what's the shape of this thing doesn't really matter. Okay, so this is the specific wave packet that we choose for our example. And if you choose this, then you will see that you can just compute the I0, the universal factor, to the leading order. And if you do high-level collisions, you will see that this factor is not only at the order of 1 over A, it is exactly 1 over A at the leading order. Okay, it's exactly 1 over the size or the area of our pancake. Okay, so the thing is that now you see that the annual probabilities will just be the cross section divided by this transverse area. And this is good in the sense that this gives us a sanity check that we are doing things correctly, because this results agree with the definition of the cross section. For example, if you open a textbook, it will tell you how to define the cross section. The cross section is basically you have 2 particle beams, and you say that the numerator is the number of scattering events, and the denominator, where this d is the density of your the particle density of your beam, and this L is the length of your beam, and this A is the cross-section area of your beam. Okay, so if you see, if you do it like this, so this is the definition of your cross-section in quantum field theory textbook, for example, in Peskin and Schroeder. And if you do this, you see that what you can manipulate is that here this dA LA times A, so so LA times A, so is the length of the beam times the area of the beam, which will be the volume of the beam, right? So this will just be, this volume times the density will just be the total number of particles in the beam. So you have the total number of particles in each beam, right? For us, what we are scattering are just 2 single particles. So for us, in each of the beam, there is just 1 particle, right? So it's 1 here and 1 here. And what is the expected value of scattering events? Then for our 2 particle scattering, then the expectation value of the scattering events is just the probability, right? So in our setup, this is just P times the probability times the area. So you see that from definition, you know that you should get P equals sigma over A. And indeed, from an explicit calculation, we do get P equals sigma over A. And we can measure it exactly because we are choosing a roughly uniform pancake. We are saying because this definition relies on the fact that the particle density in the beam is uniform. Okay, so this is why we think that this specific example of wave packet is useful. However, just remember that this is just an example. The general results in our paper are actually independent of our form of the wave packet, as long as we are taking the limit, the plane wave limit. Okay. So now basically we have everything. Then let's see. Yeah, the thing is that we know that in the end we want to project out the elastic final state, right? So we have this final state out, which is a complete final state. It's the S matrix acting on the initial state, right? And we do a projection operator here. Now we want to construct what our final state density matrix is. And just like in the initial state, in the end, the density matrix in the final state should normalize to 1. We know from the we know that if you construct the final density matrix using a complete final state, then if you just do that, then the trace of that is 1 because the unitarity of the S matrix, right? However, when you project out only the elastic part, then this out elastic, this final state will not be normalized correctly anymore. Okay, so therefore, if you want to construct your final state density matrix only using the elastic part, you will need to have additional factor. Okay, so here you see that this additional factor is just 1 over the 1 minus the probability of the inlet density scattering. And one thing I need to stress is that remember what are the probability here? The probability here are this universal factor times the scattering the cross section, right? And we say that this universal factor is scales as delta t squared. It has the size of the inverse of the inverse of the transverse area of our wave packet in momentum space, right? We know that in the plane wave limit, this will go to 0 because in the plane wave limit, we know that the wave packets in the position space is extended into infinity. So this area will be infinity. So 1 over the area will be 0, right? So the other way to say is that the plane wave limit is going to the limit where our initial states are the momentum eigenstates, which means that the weights in the momentum space are going to 0. Okay. So we know that in the plane wave limit, this is going to 0. Therefore, in the plane wave limit, all of these probabilities, scattering probability, are small. Okay, so remember that even this total scattering probability is small because the outcome is dominated by no scattering at all. So all of these probabilities are small. Okay, so because of that, as long as you want the results in the plane wave limit, what you can do, for example, for this factor in front, is that you can actually expand this probability or in the denominator to the numerator because this is small compared to the 1 part. Okay, so this is basically everything we need to have, and then now we want to.
So this is equivalent to demand that the amplitudes are perturbative.
We don't need to require that. Yeah, we don't, and we will see. And
you require, but
yeah, we will see. We don't need to require that. So the point of the result here is that the only perturbative expansion that we are doing is the plane wave limit expansion. We have not done, and we will not need to do any of the expansions in the coupling.
okay.
Okay. So we'll see why is that. So now we want to compute the final state entanglement entropy, right? And so how do you compute it? You compute it from this final state density matrix. And for example, there are a lot of like measure of the entropy. So for example, let's choose a very simple one, which is called the linear entropy. So it's just 1 minus the trace this density matrix squared. Okay. if we use the linear entropy, then you can compute the final entanglement entropy. Again, so remember this is in the linear order in the plane wave limit. It is something like this. You
What
have
does the linear entropy measure?
Mhm.
What does the linear entropy measure?
So it's similar. I would say that the people I think the most familiar with is the von Neumann entropy, right? But so this thing is similar to von Neumann entropy in the sense that if the von Neumann entropy increases, this thing increases as well. But
This is a pure state that you have here. So in what sense is there some?
Okay, sure. So this is a pure state, right? So if you just plug this into that, it will give you 0, of course.
Yeah.
Of course. Then the thing is that now we are computing the entanglement entropy.
Entanglement between
So-
what?
So now we are computing the entanglement entropy between the particle A and the particle B. This is a very good question. So the thing we do, of course, here is that we compute the reduced density matrix by tracing out the particle B first. We trace out the particle B first and get the reduced density matrix. And we plug that reduced density matrix into here, and that will not be 0. So this is the entanglement entropy. And the reason is that if you trace out the B part and you're only left with the A part will not be a pure state anymore because you have already traced the B part. And if they are entangled, then that means they are correlated, right? When you trace out the B part, actually you lost some information so that your A part will not, the particle A, the state of particle A will not be a pure, A will not be a pure state anymore. It will be a mixed state.
But this row is not the row.
Yeah, so
of-
rho is not rho f, so what is rho? Can you tell us what rho is?
Yeah, rho is let me write it. So this is rho f, right? P inelastic.
You're taking p inelastic equals 0 for your calculation, aren't you?
Not equal 0.
Not equal 0, you're not taking.
Yeah, it's not equal 0. I will expand it. To the order that we'll see how much we need to expand it. So this of course is pure state, and the trace of the rho f squared trace is 1, so that entropy is 0, of course. Then the thing is that we want the entanglement between A and B. So what we do is that we have the reduced density matrix, which is just that you trace all the information of particle B out. And then,
Is that meant to be some sort of heuristic notion of a trace or?
Is that the integral, is that what's the trace there? Is that a
yeah,
discrete sum or a
the
continuous
trace
sum?
or, let me think,
Trace is sum all possible states of.
Yeah, I understand, but is it actually the integral over the momentum states? or-
yes, exactly. The operationally, that's how you compute it, exactly.
So there's an integral.
Yes, exactly. You do this trace. And for now, we are not introducing more quantum numbers, and later we will introduce more quantum numbers. So there will be a sum of other quantum numbers as well. But for now, it's just integral over the momentum, exactly. And then this is the basically the relative density the relative entropy for particle A is computed just using this reduced density matrix square. Okay. So you trace out the information of B here, then this will not be a pure state density matrix anymore. And then you use this density matrix to compute the compute the entropy. And they will not be 0 anymore. Okay.
Sorry, are you claiming that trace is well defined outside of perturbation theory?
Yes, so because it's just the final states, right? It's just the external final state, and yes, and in the end, it's just the integral of all the possible basically a space integral of your final state. So, right. Yeah, these are very good questions.
So the K there is the momentum of A.
Yeah, so we are in the center of mass frame, so it's the size of the momentum for both of the particles. We are in the center of mass frame.
You're summing over B moment, okay.
So this K is the initial state momentum, right?
Initial.
Yeah, initial state momentum. Of course, from momentum conservation, it's the same as the final state momentum because we are doing elastic final states, right?
So what is the difference? Square root of S is what?
Square root of S is the center mass energy. Okay,
Mhm.
so
They are related.
Yeah.
Because, sorry.
Yeah.
Are massive part.
So the thing is that now at the leading order in the plane wave limit, this is the linear entropy. Okay, so and then remember that this universal factor is scale size as delta t squared. So you know that this linear entropy is actually yeah, I think I should stress this point, which is if you take the exact plane wave limit, then the scattering probability is 0, right? Because your wave packets are spread out in the whole space, in the whole position space. Then the probability that any of the two particles may meet each other and scattering is 0, right? So in the strict plane wave limit, the probability is 0. The entropy should, of course, should also be 0 because the initial entanglement entropy is 0, right? So if there's no scattering, the final entanglement entropy is 0 as well. So you see that at the leading order in the plane wave limit, this entanglement entropy scales as delta t squared. So in the end, if you take delta t to 0, then this entanglement entropy will go to 0 as well. Okay, and now you have two terms. These two terms have different origins. Okay, firstly, there is this 2 sigma inelastic. So I write it this way, and but it really comes from it just comes from this normalization factor. Remember, we say that here P inelastic is small because it's also all the delta t squared in the plane wave limit, right? So what you do is that you do an expansion in the plane wave limit, and then it go to the numerator. So this is just saying that from this normalization factor, you have this term. So this term just comes from this P inelastic part. And this first term actually comes from the numerator. Okay? And you see that it's linear in the transition matrix. Okay, and here this MF is defined as this MF is just the forward amplitude, which means that it's the amplitude, the 222 elastic amplitude with forward kinematics. Okay, so we have the imaginary part of that and so on and some factors. Okay. The thing is that you know that actually, if you do this, if you expand this numerator, you should get multiple terms, right? You know that because this all state is constructed using the S matrix. The S matrix is has one part and has a linear in T part, right? So you know that the density matrix should have like one part, linear in T part, and a quadratic in T part, right? And now you have a rho squared, so it should has like linear one part, a constant part, a linear in T part, a quadratic in T part, and a cubic in T part, and quadratic in T part, right? So therefore, you should have like multiple powers of the scattering amplitude, right? Because for each of the transition matrices, in the end, it's measure scattering amplitude. The thing is that here we only need to keep the linear in scattering amplitude part. And this is not because we are doing a perturbation in coupling. This is only because we are doing a perturbation in the plane wave limit. Okay, the higher order terms in the scattering amplitude, or the higher order terms in the transition matrix, they are all higher order in the plane wave limit. So in the plane wave limit, we can drop them. Okay, therefore you see that in this computation, we don't need to assume any of the, we don't need to assume that this scattering amplitude is tree level or anything like that. We don't need to expand it in terms of coupling constants. So this is to all loop orders. Okay, and then in the end, then remember that because of the unitarity of the S matrix, we have the optical theorem, right? We have the optical theorem that relates this imaginary part of the forward amplitude to the total cross section. Okay, so in the end, what you have here, the first term is 2 times the total cross section. It comes from the numerator. And then the second term here is 2 times the inelastic cross section. It comes from this normalization factor. Okay, they actually come from different origins, but it turned out in the end, they exactly cancel each other so that in the end, you are left with the elastic cross section. So this is our key result, which is that in the entanglement entropy, it's proportional to the elastic cross section. Okay, and here we have the universal factor I0, and remember at the leading order I0 times the elastic cross section is just elastic probability. So what we are also saying is that this entanglement entropy is proportional to the scattering probability of up to a simple numerical factor. Okay.
Can the von Neumann entropy of the reduced density matrix also be expressed in terms of the elastic probability?
I hope, but it's not easy to compute. The thing is that indeed, in the end, I would say that it would be best if we have like, if we can compute the von Neumann entropy, but it is hard as long as you are doing. It is hard because we are having a density matrix of infinite continuous we have a continuous Hilbert space, right? It's the infinitely dimensional density matrix. Okay, as long as that's the case, it's hard to compute the von Neumann entropy, and basically the main difficulty here to compute the von Neumann entropy is that taking any perturbation does not commute with the the thing is that okay, I think I will go a little bit further and answer your question. So here, firstly, if you remember, we have the example of the uniform pancakes, right? If you use the uniform pancakes, the entropy is just the is proportional to the elastic cross section over the transverse area of a wave packet. Okay. And also, there are other measures of the entropy. For example, you can generalize this in linear entropy to the nth order Charles entropy, or you can compute the Yin entropy. It turns out that this, if you are doing the plane wave limit, then you can directly generalize them. And for both the nth order Charles and the Yin entropy, it turns out that it is proportional to the elastic cross section with this universal factor and the simple numerical factor, where this n is just the nth order Yin or Charles entropy. Okay, and then there is this thing called the replica trick, which is saying that if you take the n to the 1 limit, then you get the von Neumann entropy. But you see that if you take the n to the n to 1 limit, then this is divergent, right? So so this is the main difficulty here, because this taking the limit of n to 1 does not commute with any perturbative expansion. This is the main reason. And and also I would say this is pretty well established. People also, for example, have tried to compute for example, tree levels density matrix and try to compute the tree level like von Neumann entropy. But again, people say that you cannot use the replica trick. You cannot just take n to 1 exactly because there you are doing perturbation in the coupling, right? So in the perturbation of coupling also does not commute n to 1 limit. I think it's a very good question of whether the von Neumann entropy will also give like the similar form like this. But this is something that we're still considering. Yeah, but now we still see that for a very general class of entropy measures, namely the nth order Charles and nth order Yin entropies, here we can do the perturbative expansion and get this simple result where the entropy is just proportional to the elastic cross section, or it is proportional to the elastic probability. Okay. All right.
How would the answer be different if you were in free theory?
Then there's no in free theory there is no scattering, so then there's just no entanglement.
I mean, if you just took 2 electron fields and if you took a 2 electron state and do this computation just in the out state without any scattering.
I would say that if it's a free theory, then the scattering matrix is just 1, right? So in the end, your final state is the same as your initial state. Then our initial state do not have any entanglement. Then your final state is
If you considered an initial state with entanglement.
Then our final state entanglement will be the same as the initial state. Again, because there's no scattering at all for the inner free theory.
Yeah, so I see.
Okay. And the thing is, there actually is something more interesting here, which is that we can do something that is more general. Again, we want to compute the 2-to-2 elastic process, but now we're introducing more quantum numbers. So firstly, we still say that the particle A and particle B will be distinguishable, okay, and by some quantum number, and which we will call charge, but it does not really have to be charge. It can be, for example, mass and or the total spin or things like that, okay. And then again, we have the kinematics described by the momentum, and then we can introduce some other quantum numbers, which we will call flavors. Again, it does not have to be flavors. So this is just a name that we are calling it. It can be, for example, spin or the color or anything that you want. Okay. So we are saying that for example, for particle A, it can have some flavors, and for FA, and for particle B, it can have some flavors, FB. Okay, and the FA and the FB does not have to be the same. For example, you can consider, for example, the Compton scattering. For Compton scattering, so E plus gamma to E plus gamma, for example. And then the charge, you can either say it's the electric charge or the mass. Either way, you can distinguish what E plus and what gamma is, right? And then for the flavor, it can be the spin, right? So then the flavor of the E plus will be the spin 1/2 plus 1/2 or spin minus 1/2 in some direction. And the flavor of particle B will be spin plus 1, spin minus 1 in the helicity, right? The helicity, right? So that's what we are doing here, okay? And for example, if you do another example is E plus E minus, then you can say that the charge is the electric charge and the flavor is the direction of spin as well, right? So now we are saying that now if we have the initial state, now we can the initial state is, not only has the wave function that describes the kinematics, it also has this I and I bar. These describe the flavor states. Okay. And again, and for these flavor states, these are the internal quantum numbers which are discrete, so they normalize to canonical deltas. Okay. And again, we are considering initial state with no entanglement at all. So you see that it is a product of the kinematics of particle A and the flavor of particle A, the kinematics of particle B and the flavor of particle B. Whenever you see a bar here, it means that it is a flavor of particle B. Question?
How do you know the Hilbert space you're working in carries a representation of the non-perturbative S matrix?
What do you mean? So
I mean, the entropy gets going to depend on what Hilbert space you're in, and you're telling us there's a representation of the non-perturbative S matrix in this Hilbert space.
Right, I would say that this is our assumption. Our assumption, we don't assume. The assumption for our theory is that it has asymptotic states that can describe by the momentum wave function and some quantum number. This is our assumption. Basically, this is the only assumption that we have for our theory. It has well-defined asymptotic states with quantum numbers. This is our assumption. Yeah.
Which means that it has nothing to do with perturbativity or non-perturbativity.
Right.
There's no long-range interaction. So you say that your argument is applicable.
Are you thinking about, for example, in like the infrared divergence, something like that? Because indeed, if you have, I think this is a very good question. So because we all know that if you have long range faults, for example, if you really do E plus E and E minus, there is the problem of the infrared divergence, right? So basically, you say that E plus and E minus, these are not really well behaved asymptotic states, in the sense that you know that if you have E plus here, it is surrounded by the vacuum is polarized around it, so that the E plus itself, the bare E plus itself is not a good asymptotic state, right? And the thing is that this is something that I would say this is a problem that is basically separate from what we are doing here. So here, what we are doing is assuming that we already solved all of this problem about how to define reasonable, sensible asymptotic states. For example, in terms of E plus E minus, the Euro procedure is saying that in the end, your detector will have like a finite resolution about the energy, right? So if you have solar photons that are with low enough energy, it will not be distinguished from no photon at all. So this basically there you make a infrared card, so that there in the end you will be able to get the good asymptotic states without the without the infrared divergence, right? But this is basically a separate problem. We are basically assuming that these kind of problems are already treated, okay? And after that, we say that as long as we have good asymptotic states, then what we can do.
But the initial state cannot be entangled.
Yes, you are right. Yeah, right. This is a very good point. So here the thing is that in our paper we do the most general case where we say that we can have an entanglement between the initial flavors. This is what we did in our paper. And the interesting thing here is that if your initial state is entangled, then your final state will not have the most simple form of the entanglement entropy is proportional to the cross section. It's only when your initial state has no entanglement, then your final state will be proportional to the cross section.
QCD, the initial state can be entangled.
Right. Right. So this is a very good question, and I think it provides some insight. So here the general theme here is that the entropy is proportional to elastic cross section if the initial state is not entangled.
So I think in general,
in general you can have entangled.
Simple formula applies to finite range interactions.
Yeah. So for example, if I think this will be better explained here. So in the next slide, so you see that your initial state is described by basically for at least four. You can separate your Hilbert space into 4 parts. There is a part about the kinematics of particle A. There is a part of kinematics of particle B, and there is a part of flavor particle A and flavor particle B. Right. So here your Hilbert space can be divided at least into 4 parts, right? So now when you are thinking about the entanglement, it's the entanglement between one part of your Hilbert space and the other part. So now, which is this part that you define? Actually, there are different ways to do it, right? So you basically have these 4 parts, and you say that some of it is one part, and the rest of it is the other part. And it turned out, and you are basically cutting this cake. There are different ways to cut it. So for example, you can just think about that the particle, all the information of particle A is the one part, and all the particle, all the information of particle B is the other part. And then this is basically computing the entanglement between the 2 particles, right? And if you do that, and if you assume that there is no entanglement entropy at the beginning, then again you see that in the end, this is the entanglement entropy will be proportional to this universal factor times the elastic cross section. But now, what do we mean by elastic? Well, here, what we mean is that the initial state is has 2 flavors, I and I bar, right? The final state includes any of the flavors. So, for example, if it's E plus E minus with both of the spin up initial states, then the final state is E plus E minus and I with all spin configurations. That's what we mean by elastic here. Okay, and this is what you can do for the entanglement between particle B and particle A. And like you suggested earlier, so the 2 flavors may be entangled, right? So if you do that, then in the end, if you have initial flavor entanglement, then the entanglement entropy between particle A and particle B will be non-zero. If you do that, then you see that the final state will again, the leading order results will again be scaling as delta T squared, but it will not be just a elastic cross section anymore. It's more complicated. And it's only when the initial entanglement entropy is 0, then you have the 2 terms with the total cross section and the inelastic cross section, and this conspire to give you the elastic cross section. Okay. And then there are actually other ways to cut the cake. Like for example, you can say that what is the entanglement between the flavor part and the momentum part? So the thing is that here if you compute this and assume there is no entanglement in the beginning, then again your final state will be proportional to this universal factor times the elastic cross-section. However, this elastic cross-section is not the total elastic cross-section anymore. It's an elastic cross-section where both the flavors changes. For example, if it's E plus E minus with both up spin, then this elastic final state with the flavor changing is, which means that you only select both down part in the final state. Okay, so this is very interesting. And the other thing is that here, like you said, if you assume that initially the flavor of particle A and particle B are entangled. However, the flavor space is now entangled with the momentum space. Then when you cut your cake like this, then your initial entanglement entropy is still 0. Because the entanglement is only between flavor A and flavor B, but here you are computing the entanglement between the momentum and the flavor. Then no matter how the flavors are entangled in the initial state, the entanglement between the kinematics and the flavor is still 0. If you do that, you will see that it is 0, and in the end, no matter whether the flavors are entangled in your initial state, in the end, your final entanglement entropy will still be in this very simple form. Okay. And again, there is another way to cut it. For example, you can consider the entanglement between the flavor of particle A and everything else. This is something that you can do as well. And if you do that, and again, you assume there is no entanglement entropy in the beginning, then in the end, your final state entropy will be again proportional to a universal factor times some elastic cross section. But now this elastic cross section is the elastic cross section where the particle A, the flavor of particle A changes, and the flavor of particle B can change or may change or may not change. For example, if you have E plus E minus with both spin up as your initial state, then this includes the final state where the particle A is spin down. However, the particle B may include both spin up and spin down. Okay. So you see that it's very interesting here that different ways to cut your to define your entanglement entropy actually lead to different selections of your elastic final state. Okay. And yeah, I think I don't have time to talk about the mixed state, but we do have some interesting results there as well. Okay, and let us summarize. So what we achieved today is saying that just from very basic ingredients. So we have distinguishable particles. In particular, we have good, well-defined asymptotic states with some quantum numbers that we can differentiate them. And this is our first assumption. The second assumption is that we have a unitary S matrix. The third assumption is that we are taking the plane wavelet. So then from these simple ingredients, we are able to compute for a large class of entropy measure, namely the nth order Charles and the Yin entropy. We are able to compute the entanglement entropy as proportional to the cross section, or it is just the probability with a simple numerical factor. Okay, so our result is general and non-perturbative in coupling. You see that the only perturbation we are doing here is the plane wave limit perturbation. We are not, so this is we have minimal assumptions about the theory, and this is up to our loop order. Okay, and the first we may want to say is that maybe we are saying that the entanglement entropy is the cross section is an area. So maybe we want to interpret this as an area law. So then, what do we know about the inclusive cross section, right? So actually, people know about the properties of this cross section for a long time. For example, very early on, Froissart and Martin has derived a bound on the growth of the total cross section when you increase the center of mass energy, and this growth is bounded by log squared of the center of mass energy. Okay. And actually, also very early on, like in 70s, Chen and Wu actually computed that for a general theory, this actual growth actually approaches log square s. Not only that, and this bound is for total cross section. And it turned out that they have an argument that for a general theory, the elastic part in the total cross section will approach 1/2 in the high energy limit. And actually, this behavior of growing when the cross section, the growth of the cross section when you increase the energy. This is actually observed in experiments. For example, if you look at the reviews, for example, like review particle physics, they will have a chapter of all the collider and as well as like cosmic ray experiments where they really have the hadronic total cross sections and the elastic cross sections, and you see that they do grow in the high energy limit. Okay. And if you say that now, if we say that now the electric cross section is growing in the high energy limit, and it is also proportional to the entanglement entropy, then this is basically saying that if you put more energy in the system, actually the entropy grows. So you may want to interpret this as some kind of the thermodynamics, right? So now the question here is that if you want to interpret it as an area law, so this is an area law that is very different from all of previous area laws. Well, because for previous area laws, these are for extensive system. But here we are only consider a two-body scattering. Then if you want to think about it as an area law, so the first question is what is the boundary, right? So usually when we say it's an area law, it's the area is the boundary of something. For example, for black hole is the area of the horizon, right? So if you want to interpret this as the area law, then what is the boundary? Secondly, maybe this can be related to the holography, or it may be related to black hole in some sense, right? Because so recently people actually have discovered that the black hole scattering is very similar in some sense to fundamental particle scattering, and this may provide another connection between the black holes and fundamental particles. Okay, and also this is the we have only restricted ourselves to 2-to-2 elastic scattering, but there are also other things we can do, for example, for identical particles. Because here, what we have defined is for the two initial particles with that are distinguishable. So what happens for identical particles, right? For example, in the releases experiment, when you observe the particles, you all actually observe the momentum as well. So and there is a wave function collapsing. It's collapsing to a specific momentum. So what if we do that, right? And also, what about the other final state? For example, the inelastic final state. For example, what about the three-particle final state? Can we define some kind of entropy there and see what's going on? And also, here all we have derived about the plane wave limit, and it's natural to ask what happens for the sublinear order in our perturbation, right? So that's all. Thank you.
Yeah, quick one. So you mentioned the Froissart bound, and maybe you can just go to the previous slide. Sorry, and so actual growth per log square as with sigma elastic over sigma total goes to 1/2. Does that, in that limit, what does your measurement of the entanglement entropy approach? Does it approach some?
Our derivation is independent of this, right? So our derivation is independent of this. Well, our derivation just says that the entanglement entropy will be proportional to the electric cross section, no matter what the energy is. Right? So no matter what the energy is. So this growing behavior, that means that we can just directly translate this growing behavior to the growing behavior of the entropy.
I see. Okay. Thanks. There are no more questions. Let's thank our speaker again.